We've done all of our curve sketching, we practiced it, we have our first derivative that says things are increasing, decreasing, our second derivative that says concavity, and right now we have a really good way of finding maxes and mins. We find a maximum, if we do our first derivative test, we do our first derivative, right? And you have f prime of x, and you had a point, and it went like this, you're like, it's a maximum. And it's such a good way to find a maximum. But the curriculum also wants you to know a second way to find a maximum that's not as good as the first way. Which is sometimes frustrating, because if you have a good way of doing something, you will always do that, and you'll never do a second way. And yet they have a second way, and they will test you on it specifically to make sure that you understand. Okay? The confusing thing about the second way to find maxes and mins is it's called the second derivative test. And your brain, whenever you hear the second derivative, will go to concave up and concave down because that's what it should. Because when we draw our number for our second derivative, we would have points on there, and then we would either have concave up or concave down. What the second derivative test is going to say is pretend that you know this value, but you didn't know these arrows. All you know is the first derivative is equal to 0 at c. And then on your second derivative, you know where c is on this number line. So let's say c is here. And you know the value of the second derivative at c. In this case, it's negative. That will be enough to tell if it's a maximum or a minimum. Now, normally, you would use your first derivative and say, oh, I look at my arrows and I can tell it's either a maximum or a minimum. But if I only gave you this information right now, if I only told you I know the first derivative is equal to 0 at c, and from my second derivative, I know that c is here. Is this going to be a maximum or a minimum? Now, it would have been so much easier if I had this part, right? If I had that part, you'd say right away it's a minimum. But the way that we can tell without that information, and you're asking why wouldn't I want to know that information? You're right, that's a good question. Because you could easily find that information, and that's why the first derivative test is liked by students so much more, because it's just easier. But the second derivative test says, if it's equal to 0, and when I find out where c is on my second derivative, if it's concave down, well then, can you see that it would have to be a maximum? The only way that it could be equal to 0 and concave down is if you have a maximum. If it was equal to 0 and concave up, well, your little diagram here tells you it's a minimum. This is the second derivative test. The first derivative has to be 0. If the second derivative is positive, meaning it's concave up, well, that little diagram of concave up automatically tells you minimum. If the first derivative is 0 and the second derivative is negative, concave down, this little diagram tells you, oh, I have a spelling mistake. This little diagram tells you that we have to have a maximum at x1. Is it spelled wrong on yours too? Kind of makes sense that something was wrong when you had a minimum with both situations. So obviously this would still be better because you do it naturally. And the problem is when we go through the steps of curve sketching, we find our first derivative, we draw our number line, we do increasing and decreasing. So the second derivative test is very rarely a situation. Because in normal curve sketching, you would always just use your first derivative test. But there will be questions on the exam that say stuff like, oh, if f prime of 3 is equal to 0 and f double prime of 3 is 72, what can you tell me about the point 3 comma 8? And you'd be like, oh, since it's positive, I know it's a minimum. And they'll ask questions that specifically use a knowledge of the second derivative test. So how do we use the second derivative test if the question was direct like this? Just use the second derivative test to find stationary points. Well, first you would find your first derivative. You would set it equal to 0 and factor it. And you would find that it's equal to 0 at 0 and 2. And then since you're not curve sketching and you're not worried about it, you don't even make the number line for f prime. Although normally you would. If you had to curve sketch, you would right away make your number line for f prime, put 0 and 2 and check where is it positive and negative. But instead, now we go right away to our second derivative. And factor this out. Set it equal to 0. And we get x is equal to 1. And we don't even need to make our number line for our second derivative. But what we can tell is that at x equals 0, f double prime of 0 is negative 6. At x equals 0, we have concave down. And so an understanding of the second derivative test would say, since f prime of 0 is equal to 0, and f double prime of 0 equals negative 6, which is less than 0, we know that the point 0, comma, negative 2 is a local maximum. And again, drawing this little thing down, right, when it's negative, you've got your sad face, it's going to be concave down. That concave down part tells us that it's a maximum point. And similarly, we can look at x equals 2, f double prime of 2 is equal to positive 6, which would make this concave up. And we can write another statement, since f prime of 2 is equal to 0, and f double prime of 2 is equal to 6, which is bigger than 0, we know that 2 comma, and if I want to find out what the actual coordinate, I'm going to have to plug it into the equation. 8 minus 12, negative 4 minus 2, negative 6. That 2, negative 6 is a local min. And this is the second derivative test. Is it faster than the first derivative test? I don't think so. And sure, you find it, but if you wanted to actually graph things, you'd still have to go back and do the stuff that we skipped. So usually I would say the first derivative test is better. Okay? but there will be questions that test your understanding of the second derivative test. And the second derivative test is not it uses concave up and concave down, but the second derivative test is still about finding max and min points. So if we go to our second example here, with our second example, we find the derivative, we find out where it's equal to 0. 0, -1, and 1 have the possibility of being maxes, mins, or stationary points of inflection. If we skip over our number line for f prime of x, and then directly go to, here I'll do it right beside, f double prime of x, well, f double prime of x will be 60x cubed minus 30x. Set it equal to 0, factor out 2x squared minus 1. We don't even need to find out where the second derivative is equal to 0. I can solve this, but I'm not making the number line at all. If you did want to solve this, this would, again, this would equal 0, and this would equal 1/2, so x would equal plus or minus the square root of 1/2 if you wanted to solve it. But for your second derivative test, okay, for our second derivative test, we would have the point you would have to, f prime of 0 is equal to 0, and f double prime of 0 is equal to 0. Technically, this is enough to say that this has to be an inflection point. Personally, I would like to show at 0 it changes from either concave up to concave down or vice versa. But now that we have our second derivative test, this stationary point, if it's going to be a max or a min, then the second derivative has to equal something other than 0. But in this case, the second derivative's also equal to 0. Does that show enough? No, I think I still have to show that it changes from concave up to concave down. So we can look at plugging in 0. Here we would have negative square root of 1/2 and positive square root of 1/2. They're very small numbers. You would have to plug in something close to 0, but less than the square root of this, which is 0.707. So since this 0.707, I could plug in 1/2. 1/2 squared would be 1/4. Minus 1, this will be negative. This section's negative. Concave down. Ooh. This section is also negative if we plug it in. It would be, wouldn't it? No, this side would be positive. This side, oh my goodness. Mental math disaster at this moment. Let's go a little bit slower. I plugged in 1/2. With 1/2, this is negative. This would be positive. That is correct. A negative times a positive is negative. this section's negative, concave down. If I plug in negative a half, this section right here is now also negative because it's squared. This section is still negative, making this section positive, yes. It does change from concave up to concave down at that point. So second derivative test actually does not figure out inflection points. Stationary points of inflection, we're still using what we did before, showing that it changes from concave up to concave down at that point, or it would have been enough to show that it stayed increasing or stayed decreasing at 0. But our other points, for example, -1 comma, and again, we'd have to plug it into the original equation, so we'd have -3 plus 5 would be 2, is a local, and I'm going to leave a space because I don't know yet, since f prime at -1 equals 0, and f double prime at -1, if we plug in -1 into the second derivative, we are going to get -60 plus 30, -30. Which is less than 0, less than 0. So at this point, I can fill that in to be a local max. So the second derivative tells us if it's a max or min. And the last point, 1 comma, again, look at the equation, 3 minus 5, 1 comma -2. Figure this one out. F prime at 1 is equal to 0. And f double prime at 1, if I plug that into my second derivative, 60 minus 30 is equal to positive 30, which is greater than 0. That will make that one a local min. This is our second derivative test. Okay? So, the last two. Let's do them up on the whiteboards. Get into small groups of 2 or 3. Try the last two. Once you have a solution, I'll check it and see if you can go on to the next. Learning. So the first one, almost everybody got that done. If you're using the second derivative test, technically, all you need to find is your first derivative and your second derivative. Find out where your first derivative is equal to 0. And then, once you found out where it's equal to 0, find out what your second derivative is equal to at that point. It's a positive number. That means it's concave up, meaning you'll have a local minimum, and you find your point by plugging that -1 back into the original equation. For the second one that you were working on, lots of groups got this one done too. We find our first derivative and our second derivative. Our first derivative, once you get rid of negative exponents, all you have in your numerator is a -2x. So it's equal to 0 at 0. And we can plug 0 back into our original equation, and we know the point is 0, 1. So now, is it a maximum or is it a minimum? We take our second derivative, which I did simplify here. If you plug 0 into it, you get -2. -2 means that it's concave down. Concave down means we have a local maximum. And this is an old exam question. Consider this function, part of the graph is shown. Find the derivative. So part 1, finding the derivative, would be relatively easy. Find the x-coordinate of m. Okay, m is a maximum. If you factor this, and you get -5 and 1, because the graph is given, can you see that it has to be the -5? So we're allowed to cheat a little bit here. Don't have to find out that that's a maximum to find that value. If you want to find the coordinates of n is your inflection point, you would need to find your second derivative, set it equal to 0, and get x equals -2. So you'll often find on the exam, in the curve sketching stuff, they'll ask questions like this, because curve sketching in its entirety is a long process, right? You have to find derivatives, do the number line, show increasing, decreasing, find the points, do the second derivative, find inflection points. And so a single graphing question can take 5 to 10 minutes. So on an exam, they tend to do more stuff like this. Ask you just specifics about graphing, and sometimes they'll give you the first half of the question, you have to figure out the second. The line L is tangent to the curve of f at 3, 12. So we have some point on here, the curve, somewhere there's 3, 12, and we want to find that tangent line. What would we need? We need slope and a point. We can find the slope from our first derivative. If you plugged in 3 into your first derivative, you would get 16. Then, if you have a slope and the point, you can either use the point-slope form, or y equals mx plus b, and plug in and solve for b. Either way, you get y equals 16x minus 36.